We're good? Okay, without further ado, it's Hugo and his colleague. So thank you very much.
Everyone hear me? Okay, cool. Yeah, nice to be here. Margarida and I are going to talk about the work we've been doing at CMU about automatically optimizing network Rulesets. And that is going to be more academic than most of the other talks. We hope that the tool that we're developing will be useful for a lot of you. Okay. So if you're here, you probably know what a virtual switch is. If you don't know what a virtual switch is, you're probably in the wrong room. But in this talk, we're going to focus on a particular aspect of virtual switches, which is their ability to implement SDN policies. So like a common example is like virtual switch, open vSwitch, but there are also other proprietary solutions like VFP used inside Amazon and Andromeda used by Google. And all these virtual switches they have in common is that they provide this somewhat similar abstraction for policies. And that is, given a packet and a rule set table, so a list of rules, give me the first rule that matches the packet. So like the rule with the highest priority. So naively, you could like implement this by scanning the list of rules sequentially until you find the first one that matches, if they're sorted by priority. But if you use this as you scale the number of rules, the runtime will also scale poorly. So instead, what people do is that they use these data structures we call packet classifiers. A common example is double space search, which was proposed in 1999, and it's also the one that OVS uses. But there are also other more recent ones, like partition sort, tuple merge, and wave match. There's all sorts of techniques to make this packet classification faster. But the key takeaway here is that there are decades of research, and state-of-the-art classifiers are actually pretty good. They can do as much as 2.5 million packets per second using only 100,000 rules. So one may think that like in practice you will have a performance that is just as good. But the reality is more complicated. And that is because SDN policies are more complex than these packet classifiers papers often assume. And the reason for this complexity is that operators often need to apply multiple actions to every packet. So for example, you may have, like, you may want to do tunneling, NAT, and then echo. And the way you implement this is by mapping each one of these stages to a different table. And each one of these tables needs their own dedicated classifier. So instead of like the model I showed before, where a packet comes, we go through one classifier, and we decide the policy, we actually go through many classifiers before we're done. So to show that this is a problem, we look at 20 different production rule stacks, both from Microsoft and from NVIDIA, and we saw that the median number of table servers was at least 13 in all the rule stacks that we saw that we look at. And not only this, we saw that the size of these tables also varies dramatically, with most rules often concentrated in few tables. So you usually have more than 10 tables, but the majority of rules concentrate only a few of those. We also look at how the performance is affected by the structure of the rule set. So we saw that there are two main characteristics of the rule set that influence the performance. So one is size, which is probably more intuitive. And that is the more conditions you have, the longer it takes to classify a packet. So even though you're using these packet classifiers, you still have like an increase in classification time, the more conditions you have. So here in this plot, we're using a single table, and we'll look at the classification time for different classifiers that exist. And you can see that regardless of the classifier, the more conditions you have, the longer it takes. But perhaps more interesting is that if you fix the number of conditions, in this case we're fixing to like 10,000, but we spread it equally among more tables, having more tables can actually have like an even bigger impact than just having more conditions. So here you can see that even using 5 tables with 10,000 conditions gives a performance that is comparable to using 100,000 conditions. Okay, so given the influence of the size and the structure of the rule set on classification performance, in this work, we decided to see if we could just find rule set transformations that would reduce the classification time while preserving the reasonable semantics. So instead of trying to improve the classifiers itself, can we improve the rule set itself to make performance better? And the approach we're using is a compiler optimization technique so that we can get a rule set as an input, apply these optimizations, and get a rule set back without changes to the packet classification itself. And there are 2 main opportunities that indicate that such an approach is promising. The first is that real rule sets may combine manually and written automatically general rules. So there might be a redundancy in the rule set. And real rule sets can often be restructured to reduce the number of tables that a packet needs to traverse. So both of these opportunities may lead to improvement in performance when we change the rule set. And what we're going to talk in the rest of this talk is about JetStream, which is a general tool to automatically optimize network rule sets with provable correctness. So in the rest of this talk, Margarida and I are going to talk about how we ensure each one of these properties. Okay, so the first challenge is how we actually ensure generality. Because different virtual switch implementations, they impose different constraints on how we can define and run rule sets. So here's an example. If you take OVS and VFP, which is used by Microsoft, while OVS allows you to traverse tables arbitrarily, so you match a rule and you can jump to any other table, VFP imposes a structure that we call layers that we force packets to traverse layers sequentially. They also differ in how we define matches. So OVS only allows you to do a single match per field type in every rule, but VFP allows disjunction within the same rule. And while actions in OVS are simple and predefined and very well documented, in VFP they can be arbitrarily complex and they can even change after you wrote a rule set. So it's kind of tricky to model this kind of stuff. So the first insight is that we're going to use an approach that is similar to what compilers do. We're going to use an intermediate representation so to model the rule set itself in a somewhat target-independent manner. And the first thing we do is that the intermediate representation is generous in how we allow this policy graph to be specified. So you may think of the rule set as this graph of tables. And for every table, you can jump to any other. So pretty much how OVS works. And for more restricted settings, such as the one in Microsoft, we can map to this more general intermediate representation. And we're also cautious in how we model the actions. So for simple actions, like allow block or just setting a source IP to value, then we can model very precisely. But for more complex actions, like a stateful NAT, then we just assume a black box model, and we assume that this action can make arbitrary changes to the packet. So that's like a very generous approach. The trade-off is that we might miss some opportunities for optimization, but we never trade correctness. Okay, so at a high level, the workflow also looks a bit like a compiler. We have a front end and a back end. And the front end is target specific. So in this case, I'm showing VFP, but it could also be OVS. And the user supplies a rule set in this target specific format. The front end would then convert the rule set to the intermediate representation. And then the JetStream optimizer will do a sequence of optimizations to try to improve the intermediate representation. Then the front end is responsible for converting this back to the original format. Okay, so to explain more about the optimizations, I'm going to head into Margarida.
Okay, so now that we have our intermediate representation, we can look into how the JetStream optimizer works. Our goal was to be able to automatically look into these Rulesets, find redundancies, remove them, and prove that the transformations we are making are correct. Okay?
Yeah,
oh, okay.
I guess your mic is better. My mic is better. No worries.
If you put it on
Is that better? Okay. Okay, so as I was saying, our goal is to automatically find these opportunities to reduce the rule set, make these reductions and prove that what we're doing is correct. In this case, correct means that we're not changing the semantics of the rule set. And the way we do that is by using SMT to model the rule set and then ask different queries. And SMT allows us to do this in a way that is fast, provable, and explainable. Fast because we can find our redundancies and do all our queries in under half a minute. It's explainable because whenever we find these redundancies, the SMT solver will tell us exactly which rules are causing the redundancies and why. And it's provable because due to our formulation, we can at the end prove that the rule set before the transformation is equivalent to the rule set after. So we execute two types of optimizations in JetStream. First, we do intra-table optimizations, which find redundancies within the same table of rules, and thus reducing the size of each table. And then we look for inter-table optimizations, which restructures the graph, thus making the number of tables each packet has to go through smaller. So we'll look into each of these types one by one. The first type of intra-table optimizations we do is the optimization of matching conditions, which looks for redundancies within the conditions of the same rule. Then we look for unreachable and subsumable rules, which are types of redundancies that come from the way the rules interact between themselves within the same table. And finally, we'll look into our inter-table optimizations, which are done via a technique we call table inlining. Okay, so here we have an example of one rule in our intermediate representation. We have a match field which conditions the packets that can be matched by this rule, and then we have a sequence of actions which are applied to the packet once it matches. And finally, we have the list of tables that the packet is redirected to, in this case, just one. If we look closely at this rule, we can see that the last matching field for source IP here is contained in the first matching field. So our SMT formulation allows us to find this kind of redundancy and prove that by removing it, we maintain the same semantics and we have a smaller rule. For our second type of optimization, we need to take a step back. We're no longer looking at individual rules, but instead at how they interact within themselves. So here we have two rules, and we need to remember that they are sorted by priority, which in this case means that rule x2 will only be matched if rule x1 is not. But here we see the same example, that the matching field of the source IP of rule x2 is contained in the matching field of the source IP of rule x1. This means that rule x2 in practice is unreachable because every packet that would match there will be matched by x1 first. And that in turn means that we can remove rule x2 without any loss of semantics. The third and last kind of intra-table optimizations that we do is looking for subsumable rules. We are again looking at how rules interact with each other, but this is a little bit more subtle. In this case, the matching conditions of the first rule, in this case x0, are contained in the matching conditions of the second rule, x1. So, but this is not sufficient. We also need to ensure that the actions of both rules are exactly the same, as well as the tables that the packets are directed to, and that there is no rule in between them that would match any packet that would otherwise be matched by rule x1. If all these conditions are true, then we can say that x0 is subsumable, because in this case, any packet that would match x0 and have its actions applied to it will instead be matched by x1 and have its actions applied to it. So we can remove x0 without any loss of semantics. So these are our three types of intra-table optimizations. And now we'll look into inter-table optimizations. And here we need to take another step back. We are now looking at the way tables interact among themselves and not just rules. So if you remember, Ruleset contains many tables, and each rule in the Ruleset defines actions and the next table that a packet will be directed to. So each rule can arbitrarily send packets to other tables. And what we do is called inlining. And if there is one table in the rule set such that there is only one rule in the entire rule set that is pointing to this table, we can inline the first table into the second table without increasing the number of conditions overall in the rule set. And we can do this by making the conditions of the new rules conjunction of the conditions of the old rules, and just composing the actions of the tables in the rules. And we can do this with no impact in the size if there's only one table. So to evaluate JetStream, we have, as Hugo mentioned, 20 different production rule sets. 19 of these are in the VFP format, and only one is in the OBS format that we got from NVIDIA. And we tested these rule sets using 3 classifiers that Hugo mentioned before: tuple space search, partition sort, and tuple merge. So in this plot, we have on the y-axis the rate improvement, which is just basically how much faster these rule sets were once they were reduced by JetStream as compared to how they were originally. And in the x-axis, we have each different rule set that we are using to evaluate. The first 19 on the left are the ones we got from Azure, and the one on the right is the NVIDIA rule set. Then each bar in a different color and pattern will be the different classifiers that we use to test them. So we can see that across VFP rule sets, we had significant improvements up to 70%, but in the NVIDIA rule sets, the improvements were not as significant. This is because in VFP, we could reduce the number of conditions and the number of tables in a significant manner because they were handwritten mixed with automatically generated, coming from different teams. We had a lot of redundancy there. However, in the NVIDIA rule sets, they were generated by Oven, and the tool already does a pretty good job at removing all redundancies. So there were none. However, we still found about 5% decrease in the size of the rule set, and that decrease, once we looked into what was happening, we were able to uncover bugs in the rule generation tools that they were using. We also include here the running time of each optimization that I told you about. As I said before, each of them takes under half a minute for each rule set. And then equivalence checking is the procedure that we do at the end to compare the original rule set with the reduced rule set and have the SMT prove that they are equivalent. And that takes a little bit longer, with the median time being just over 2 minutes. So in conclusion, we take a different direction, different than what was done before. Instead of trying to improve the classifiers, we try to improve classification performance by changing the rule sets themselves. We do this by using SMT, which allows us to find these redundancies fast and prove that the transformations that we make are correct. So if you have a firewall rule set and you would like to know how much JetStream can optimize it, we would be very happy to help you. This is academic work, as you know, so there will be no code until the paper is published. But if you want to know how much we can optimize it, please tell us and send us your rule sets, because we are always looking for new data to test JetStream on, and we'll be very happy to run it for you. Thank you.
Awesome. It was an awesome talk. Thank you so much for doing that work, and I learned a lot from it as well. There is this gentleman here, his name is Adrian, he's sitting right there. He should be your best friend at lunch, because this is the area that he operates in, and he's trying to help us with that stuff. So he will buy you lunch, you'll buy them lunch, right? He'll buy you lunch today, and even dinner for tonight if you want. So please work with him and talk more and see how we can integrate this stuff in our system. And this is open source, public. What's
After the paper?
It will be.
Okay. Good answer. It will be. Best answer.
Yes.
Any other questions? Yes.
So you showed how your optimization works, and it seems to me that it's like an iterative process. So you take a rule, you make it better, you put it back, and then you look again. Are there situations where you make a choice that in the end causes you to end in a rule set that's suboptimal and would have gotten you to a different rule set if you didn't make that choice? Maybe a hard question.
Yeah, that's an interesting question. There are such situations. One of the studies we did is to look into the different kinds of optimizations separately. Where is that slide that I'm looking for? This one. And we found that table inlining, for example, sometimes makes the performance worse. And this happens because by inlining tables, it might be the case that you're inlining a very small table that is very often hit into a very large table that was very and that is not good for performance. Even though we have not done this work, we think that we can run away from this problem just by knowing exactly how often each rule is hit by just getting that data from the rule sets that we have. I think other than that, the unreachable rules and the subsumable rules are always good. Do you want this one?
Oh, yeah, we can also share. So yeah, so some of these optimizations may also be workload dependent. So another thing that we're interested in is like having rule stacks that also have like the hit of every rule. So we can consider that when optimizing.
Yeah, so like a performance profile.
Yeah.
Right? Yeah. Okay.
So almost like what compilers do as well.
Yeah, exactly.
Yeah.
All right, cool. And I also had a second question. So I guess you kind of know how your optimizer behaves in normal cases. Do you have recommendations for rule writers to write the rules in a way that helps your optimizer?
I don't. Do you have?
I don't think so. The goal of the optimizer is exactly so that rule writers don't need to worry about it. All we do is look for redundancies, and I think looking at the rule sets that we had from NVIDIA and from Microsoft, it's not really reasonable to ask people to just go through all the rule set. Make sure what you're adding is not redundant.
Okay.
They're massive, yeah.
That's not something people can do, so this is why we have it.
Okay. And maybe one final question is, you talked about mainly removing redundancies, but did you think about maybe other transformations that could also help speeding up things? I don't know, just open question.
Yeah, so like related to the workload, for example, if you know that the majority of traffic is going through a particular path, maybe it makes sense even like add tables, but make sure they all go through this.
Yeah. Okay, cool.
We haven't explored this, but I think this may have a lot of potential.
Interesting. Thank you.
So I think we'll have to postpone the questions till lunch. You guys are staying the whole day, right? Yeah. So it's great that you have some. Yes.
So can Adrian pay for my lunch too?
Adrian cannot pay for your lunch. He'll pay for everybody, but not yours, Bob. I'm joking, of course. So I think it's a lot of questions are pending. So if you're going to have lunch with us, then we can get those answers. But it was a very good talk. Congratulations on a good talk, and wish you the best for your thesis defense and the papers coming out. But you did promise to make it open source after the paper. You're not going to forget about that. I know where you live. Okay. Okay.